In this module, we will discuss type 1 censoring through an illustration. We will also discuss about the random censoring and will throw some light on Kaplan-Meier estimator as the maximum likelihood estimator of survival function under censored setup. Let us begin with an illustration under type 1 censoring. Suppose the lifetime of an item follows exponential distribution with mean theta. Now, under type 1 censored data, as mentioned in the last module, the likelihood of theta will be capital L theta equal to product over I from 1 to n small f theta at ti whole to the power delta I into capital F bar theta at capital Li whole to the power 1 minus delta I, where small f theta t equal to 1 by theta times e to the power minus t by theta and capital F bar theta t equal to e to the power minus t by theta. If we define a set script A equal to set of those I such that delta I equal to 1 and hence A complement equal to set of those I such that delta I equal to 0, then we can write capital L theta equal to product over I belonging to script A 1 by theta times e to the power minus ti by theta into product over those I belonging to script A complement e to the power minus capital Li by theta. As a result, it becomes 1 by theta to the power r e to the power minus 1 by theta times summation I belongs to script A ti plus summation I belongs to script A complement capital Li, where r is equal to summation I belonging to script A delta I, that is actually the total number of uncensored cases, or you can say the number of items from which lifetimes are actually observed. Now we can write summation ti I belonging to script A plus summation capital Li I belonging to script A complement is equal to summation I from 1 to n yi, where yi are nothing but the potential responses, and that is equal to say y. Therefore, now capital L theta equal to 1 by theta to the power r times e to the power minus summation yi by theta. Now from this we can get the maximum likelihood estimator of theta as theta hat equal to summation yi by r. Now note that here r is not fixed but a random variable. It is difficult now to find the exact or small sample distribution of theta hat as its denominator r is not fixed but a random variable. This also implies that we have to therefore consider the asymptotic distribution of theta hat. Using asymptotic distribution of maximum likelihood estimator, we can write theta hat, which can also be denoted by theta n hat, converges in distribution to normal with mean theta and variance I theta inverse, where I theta is as usual Fisher's information. Now I theta is equal to expectation of minus del square del theta square of log of L theta, where L theta equal to 1 by theta to the power r e to the power minus summation yi by theta, and this implies log of L theta equal to minus r log theta minus summation yi by theta. As a result, del theta of log L theta equal to minus r by theta plus summation yi by theta square, and finally del theta square of log of L theta is equal to r by theta square minus twice summation yi by theta cube. This implies expectation taken on minus del theta square of log of L theta is equal to expectation of twice summation yi by theta cube minus r by theta square, which is equal to twice summation expectation of yi by theta cube minus expectation of r by theta square. Let us denote this expression by star. Now expectation of yi is equal to expectation of yi given delta I equal to 1 into probability that delta I equal to 1 plus expectation of yi given delta I equal to 0 into probability that delta I equal to 0. Actually here we have used the result of conditional expectation. Suppose this expression be denoted by double star. As we already know that probability that yi equal to capital Li given delta I equal to 0 is equal to 1. This implies expectation taken on yi given delta I equal to 0 is actually equal to capital Li. Also expectation of yi given delta I equal to 1 is nothing but expectation of Ti given Ti less than equal to Li, because we already know that delta I equal to 1 is equivalent to saying Ti less than equal to Li, and then yi is actually equal to Ti. Anyway, this is equal to integration 0 to Li t into 1 by theta e to the power minus t by theta times dt divided by distribution function capital F theta at Li. On simplification, we get from here that this is equal to theta by 1 minus e to the power minus Li by theta times 1 minus Li by theta plus 1 times e to the power minus Li by theta. Hence, double star gives on simplification that expectation of yi equal to theta into 1 minus e to the power minus Li by theta. Now without loss of generality, we can write r equal to summation I from 1 to n delta I, because we know summation delta I belongs to script a complement is actually 0. So this implies expectation of r, that is equal to summation expectation of delta I, is equal to summation probability of delta I equal to 1, and as we already know that probability delta I equal to 1 is nothing but capital F theta Li, and that is equal to 1 minus e to the power minus Li by theta. Therefore our expectation of r becomes summation I from 1 to n 1 minus e to the power minus Li by theta. Let us denote this expression by q, say. Hence finally star implies Fisher's information I theta equal to twice theta times summation 1 minus e to the power minus Li by theta divided by theta cube minus q by theta square, which on simplification becomes nothing but q by theta square. Therefore the maximum likelihood estimator theta n hat converges in distribution to normal with mean theta and variance theta square by q. Since theta is unknown, so q is also unknown, and therefore the maximum likelihood estimator of q will be q hat equal to summation I from 1 to n 1 minus e to the power minus Li by theta hat using invariance property of maximum likelihood estimator. Now we are going to discuss random censoring, which is most frequently used censoring in statistics. A random censoring is very similar to type 1 censoring. The only difference is that here the censoring times are also random variables. A simple random censoring process is one in which ith item is assumed to have lifetime capital Ti and censoring time Ci with Ti and Ci independent continuous random variables. Let capital Ti be IID with common PDF small f theta and common CDF capital F theta. Also let Ci, that is the censoring variable, be IID with common PDF G and common CDF capital G. Define the pair capital Yi and delta I same way as in type 1 censoring. Then the likelihood function of theta for given dataset small ti, delta I from 1 to n on the paired random variables yi delta i's will be capital L theta equal to product over I from 1 to n small f theta at Ti times G bar at Ti whole to the power delta I into small g at Ti times capital F bar theta at Ti whole to the power 1 minus delta I. We can verify this form of likelihood under random censoring. We know probability that capital Yi lies between small yi and small yi plus delta I, and delta I equal to 0 is equal to probability that small yi less than ci less than equal to yi plus delta yi, comma ti greater than small yi, because delta I equal to 0 implies an implied by ti greater than ci, and which implies an implied by yi equal to capital Ci. Now this probability can be written as probability that small yi less than ci less than equal to yi plus delta yi times probability that capital Ti greater than yi, because capital Ti and capital Ci are independently distributed. This implies with delta I equal to 0, the likelihood corresponding to ith unit will be capital Li theta equal to limit delta I tends to 0, probability yi less than capital yi less than equal to small yi plus delta small yi, comma delta I equal to 0 whole divided by delta yi, and this is nothing but the PDF of censoring variable small g at yi times capital F bar theta at yi. On the other hand, probability that small yi less than capital yi less than equal to small yi plus delta small yi, comma delta I equal to 1 is equal to probability that capital Ti lies between small yi and small yi plus delta small yi, and capital Ci greater than small yi. As now delta I equal to 1 is equivalent to saying Ti less than equal to capital Ci, and that is equivalent to saying yi equal to capital Ti. So this probability is now equal to probability that Ti lies between small yi and small yi plus delta small yi times probability that capital Ci greater than small yi. Here also the likelihood capital Li theta is equal to small f theta at yi times capital G bar at yi. Therefore, capital Li theta is now of the form small g at Ti times capital F bar theta Ti with delta I equal to 0, and is of the form small f theta at Ti times capital G bar at Ti with delta I equal to 1. Combining these two forms, we can write capital Li theta equal to small f theta at yi into G bar yi whole to the power delta I times g of yi into capital F bar theta yi whole to the power 1 minus delta I for all I. So this implies the joint likelihood function of theta based on given data set on independent capital yi delta I pairs will be capital L theta equal to product over small f theta at Ti times capital G bar at Ti whole to the power delta I into small g at Ti times capital F bar theta at Ti whole to the power 1 minus delta I. Now we will discuss informative and non-informative censoring in context of random censoring. Suppose theta be the parameter of the exact lifetime distribution, that is of the probability distribution of Ti's. If the probability distribution of censoring variables Ci's also involve theta as its parameter, the random censoring is informative, because then censoring variable also adds information about theta. Otherwise, it is non-informative. For example, Ti follows exponential theta and Ci follows exponential gamma theta implies informative censoring, but Ti follows exponential theta and Ci follows exponential phi, where phi is independent of theta, implies non-informative censoring. Kaplan-Meier estimator or product limit estimator of survival function. Let small t1, small t2, small tn be uncensored sample observations on failure times. Then a nonparametric estimate of the survival or reliability function capital St at the time point t will be given by Rn t hat equal to number of observations, that is number of Ti's greater than equal to small t divided by n. Let us denote this expression by number 1. Now this is basically the complementary of empirical distribution function at the point small t. Now consider a type 1 censored sample. In this case, the number of lifetimes or failure times greater than equal to a time point small t may not be known exactly. So we need some modification in number 1. The modified estimator, by incorporating the sense of type 1 censoring in appropriate way, is called the product limit estimate of reliability function. This is also known as Kaplan-Meier estimate from the authors who first discussed its properties. Suppose there are n items and there are k less than equal to n distinct failure times, say t1 less than t2 less than less than tk observed. Let dj equal to number of failures at the time tj. In addition to the failure time, there are censoring times capital Li for items whose lifetimes are not observed due to some reasons. Let capital Nj denote the number of items at risk of failing at the time point tj, that is the number of items that are functioning and uncensored just prior to the time point tj. Then the Kaplan-Meier estimate is defined as Rnt hat equal to product over dose j for which tj less than the point t, nj minus dj by nj, where nj plus 1 is equal to nj minus dj minus cj. And what is cj? cj equal to number of items censored at the time point tj. Now note that Kaplan-Meier estimator is a non-parametric maximum likelihood estimator of the survival function Rt. As a justification, let capital T denote lifetime of a randomly chosen item. This implies the survival function capital R at the time point t is defined as Rt equal to probability that capital T greater than small t. Let small t1 less than small t2 less than small tk less than the time point small t, and that is again less than say another time point, say tk plus 1. This implies the survival function capital Rt equal to probability that t greater than small t is equal to probability that capital T greater than t1 times probability that capital T greater than t2 given capital T greater than t1 etc. probability that capital T greater than small t given capital T greater than small tk. Let us define lambda j equal to probability that a randomly chosen item will fail at the time tj given that it survived at tj plus 1. This implies Rt equal to 1 minus lambda 1 into 1 minus lambda 2 etc. into 1 minus lambda k into 1. Because the last probability is a probability of a sure event. The last probability was probability that t greater than small t given t greater than tk. Now we all know if the lifetime t is greater than tk, then the next failure time is tk plus 1. So that means if t exceeds small tk, then t is definitely exiting small t also. So that is why it is a sure event and its probability is 1. Anyway, the reliability function Rt is equal to product over 1 minus lambda j product over dose j such that tj less than t. Now according to definitions we have already given, nj equal to number of items under the risk of failing at tj given that they survived at j minus 1, and dj equal to number of items actually failed at the time tj. So this implies dj follows binomial distribution with parameters nj and lambda j for all j. Now we know that maximum likelihood estimator of lambda j is lambda j hat equal to dj by nj from the theory of binomial MLE. This implies by invariance property of maximum likelihood estimator of Rt is that Rnt equal to product over 1 minus lambda j hat product taken over all possible j for which tj less than t, and that is equal to product over 1 minus dj by nj product over all possible j such that tj less than small t. But what is this? This is actually nothing but our Kaplan-Meier estimator. So the Kaplan-Meier estimator is the maximum likelihood estimator of the reliability function RT. Moreover, as dj always follows binomial distribution irrespective of the parent population distribution capital F theta of the lifetime variable capital Ti, this implies the distribution of Kaplan-Meier estimator is actually distribution free. That means Kaplan-Meier estimator is a non-parametric estimator of survival function. This module we have discussed already is rich in an illustrative idea on type 1 censoring under exponential life and also with a conceptual discussions on random censoring. We also studied in this module the Kaplan-Meier estimator as the non-parametric and maximum likelihood estimator of reliability function.